on a novel tool to enable clinicians like myself, and of course also non-clinical researchers who don't have a stats background and who are not proficient in coding, to actually do a robust prediction model with for clinical purposes. So I'm Roland Zahn. I'm a reader in mood disorders and honorary consultant psychiatrist, and I'm going to chair the session and also going to look at the chat if there are going to be questions. But Andrew Lawrence, who's the postdoctoral researcher working with Paola Dazzan and me, is going to lead the session, and he's programmed the software and is going to give you a practical hands-on tutorial, but also allow questions, particularly towards the end. But before I hand over to you, Andrew, and let you introduce yourself, may I just ask Daniel Starr, Professor Daniel Starr, to introduce himself, who's been the theory, who's driven the theory behind this as the head of the prediction modeling group in our biostats department. And that was fantastic to have Daniel really tell us exactly what to do with this tool and how to make it proper, statistically sound. Okay, Daniel, over to you, and then Paola, please.
Yeah, hi. I'm Daniel Stein, Professor of Medical Statistics and Statistical Learning, and my main interest is prediction modeling, and I collaborate now with Roland and Andrew for a while on predicting recurrence in depression, and I helped Andrew with a bit with his model, but I didn't really had to tell him a lot because he's very good. He's done most of it by himself. So yeah, I think that's it.
Thanks very much, Daniel. And over to Paola. Paola, please, Professor.
Hi. Thanks, Roland. I'm Paola Dazzan. I'm a professor of neurobiology of psychosis here at the Institute of Psychiatry, Psychology and Neuroscience, and I'm also vice dean for our international strategy. And it's a pleasure to have collaborated with all of you guys on this tool. I'm one of those people that Roland mentioned that does not have a lot of statistical knowledge and really welcomes the the creation of tools like this one, because as a clinician, as a consultant psychiatrist, I really value the potential of prediction tools that can really help us to identify our most vulnerable people and those most at risk. So it's been great to collaborate and to see these now presented in the workshop. Thanks.
Fantastic, Paola. And just to say, the tool is freely available on Andrew's GitHub page, and we've got a paper accompanying it to describe its methods. But over to you, Andrew. So the idea is Andrew is going to lead the session now, and then we'll have a discussion later on where you can ask questions primarily to Andrew, but the panel, so us, Paola, Daniel, and me will be able to chip in with some answers. Okay, over to you, Andrew.
Lovely. Thank you so much for the introduction, everyone. Yes, I am Andrew Lawrence. I am a postdoc here working with Paola and Roland and collaborating with Daniel. And my background is probably important. I'm not a statistician. I'm statistically aligned. I started in psychology, experimental psychology, and I currently work in sort of neuroimaging and prediction models within that. Those are my sort of general interests. So I'm going to talk today about dCVnet software. It's going to be a bit of a hybrid between an introduction of why we want to use the software, why it's important to do it this way, or why we think it's important to do it this way, and how to physically use the software as sort of a tutorial. So it's a bit of both. And as Roland was saying, the next at the end there will be a discussion panel. So at the bottom left of this slide, I hope you can all see, is the link to the GitHub, and this is really where the project, the software is coordinated from. So if you want to obtain the latest version of the code, it's always there. You can see the development version adding new features as and when we do. You can submit any problems if you find a bug. There's an opportunity to do that on the GitHub, as well as collaborate if you find a useful extension. It's all open source, and we're keen for anyone to get involved who wants to. Also, on the bottom left there is the paper. If you do end up using this software, please do cite the paper. Really very keen for that to happen. So what I want people to come away from the session with is an idea of what the software does, why it does it, and if you would want to use it in your research, how could you go about doing that? But I think this is all pretty standard. Roland's covered this. Any quick clarifications, questions, please do just butt in. It'd be good to hear from you. But if you want to save anything longer, more philosophical, we can be very happy to talk about that at the end. So dCVnet, it stands for double cross-validation of the elastic net. Oh yeah, good point. Roland, can I ask if you would mind popping in the links?
Sorry, it's fine, Andrew. I'll put the links in. Thanks, Andreen, for pointing this. I'll monitor the chat, Andrew, and if someone raises their hand, I'll tell you so that you can concentrate on your.
Wonderful. Thanks very much. Yes, double cross-validation for the elastic net. And really the idea was we wanted an easy to use tool here. I think that the key part is the easy to use tool, because this is not from a statistician's point of view, someone expert in this is not an earth-shattering model. This is not drastic new science, but there's very few ways to do this easily without a lot of programming experience and a lot of statistical experience as well. And so the idea was to create a reusable tool that we could, rather than just a simple script, that we could apply to any new projects going forward. The setting is prediction, and currently the tool uses binary logistic regression. So currently we're suitable only for prediction problems where you have two outcomes and you want to predict one outcome versus a baseline binary logistic regression. But this is soon going to change, and most of the work is done to add a lot of other families. So there will be multinomial, so more than two categories. In theory, there will be multivariate Gaussian as well, although that will need a bit more testing, and continuous measures, obviously, and Poisson and potentially Cox models are all sort of in development. And if you have problems like that, I'd be interested to hear what prediction measures you'd be wanting to know about your data. The elastic net regularization, I'll explain fully in the next section, and double cross-validation. This is also called nested, and it's because we need to select regularization hyperparameters and estimate the generalization error at the same time. And if this all sounds like gibberish, then hopefully the next section of the talk will be good for you, because I'm going to explain it all. So prediction in a clinical setting. The general setting is prediction. We have some outcome that we're interested in. It could have, I'm switching rapidly from binary logistic regression to the general case. So this could be anything. It could be a number you want to predict. It could be a category. There's some variable you want to know the value of. You're interested in the value of, and you've collected some data, some predictors, hopefully there's a way of transforming those predictors into information about your outcome. You want to know whether you can learn a function of your data that will predict your outcome. the function of the data, f of data here, is some sort of prediction model. Essentially, this is what a prediction model is, and it can be very general. It could be anything from a very simple algorithm. If your age is over this, then you should attend this screening for hypertension. That is a prediction model to a simple extent, but more widely, I think people are used to their algorithm ones like the framing and risk score, for instance, which predicts the 10-year risk of coronary heart disease. For that, you apply an algorithm related to age, cholesterol level. You look at you put your age in the bin, you're assigned a certain number of points, you put your cholesterol level in one group of cholesterol levels, and you get a certain number of points depending on what it is. You add up your points at the end, and it turns into a risk. So that is the prediction model. More commonly, we work with regression models where the values of the data are multiplied by the coefficients and added together to produce the prediction of the outcome. At the very other end of sort of model complexity, you could think of a deep learning neural network model. The observed data is propagated as activations through layers of artificial neural networks. The end result is the same, though. It becomes a prediction of the outcome, and that's never perfect. So we have the error term as well. What's special about a clinical setting? This is a gross generalization, I'm aware, but when we work with clinical data, it can be really expensive to collect more observations, and often we're dealing with small sample sizes. Sometimes it can be impractical for very legitimate reasons. Maybe there aren't enough patients in the entire world with a disease of this sort, but you don't have the observations you'd like, and that puts it in contrast to other fields where it can be relatively easy to collect more data. But what we do have usually is a pretty good background knowledge about the outcome and some, if not all, of the predictors from previous research. We're sort of rarely going into this blind with a complete black box with no understanding of what might predict the outcome. So we're interested in prediction, and this is contrasting from inference. So so a prediction setting, we're interested in how useful or accurate the prediction based on the function of the data is. So your prediction model produces a prediction. Is that any good? Will that reflect reality? And particularly, we want to know about future observations. If I go out and collect a new data set, will the predictions derived from your prediction model still be useful? And sometimes not. I'm going to talk about overfitting in just a second. This contrasts with, I think, how most people start in statistics, certainly me, where you are often interested more in inference, where you have explanatory or causal questions. So how much do the predictors impact the outcome? Is X associated with Y? These are questions about sort of what is the nature of my prediction model? What is the function of data? What are the parameters? You can also think about counterfactuals as well in this way, although it's not always valid. If you change the value of your data, if someone was actually 10 years older, what would their probability of what would their outcome be? What would the prediction be? But we're firmly interested here in prediction. So this the tool is in this setting. We're interested in coming up with accurate predictions that will be useful for future outcomes. Now, the useful for future outcomes is the key problem here, because for any prediction model, you can obtain a better prediction in the sample where you fit the model by just making it more complicated. And this is, it's a truism. It's really simple. In regression, you can add any random noise variable and it will improve the performance in that data. This is why there are things like adjusted R squared in an inference setting, but it's the same with neural networks. If you have enough parameters and not enough training data, you'll just be able to encode and memorize the exact input data, and it won't necessarily perform very well in new data. And just to be clear, what I'm talking about with complexity, it's not just the number of predictors in the model, it's how you treat them as well. So if you include derived terms, so if you have a nonlinear relationship for a predictor, if you model it as a quadratic or a cubic, or you use splines. These increase the complexity. If you have interaction terms between predictors, it increases the complexity. This is all ways that you will get a better fit to your data, but not necessarily any future data. And overfitting is what happens when you have a great fit for your current data, but it doesn't work out for the next data point that comes along that wasn't used in training the model originally. Essentially, the prediction model you've generated too closely reflects the individual quirks of your particular data set. And we can measure overfitting. Particularly, very practically, it's the gap in performance between the data used to fit the model and performance in new or unseen data, and we can call this a generalization error, the error when the model is moved to a more general setting. So the issue here is overfitting is a matter of degree. So all models overfit to the data that they've seen. It's just a matter of by how much. If you have enough data in the training to train the model, the overfitting is usually less, but that depends on how complex your model is. In inferential statistics, overfitting is recognized as well, and it's the cause of high variance regression coefficients, which can show these large and unstable changes when you have small differences in the data set. So you might drop a couple of subjects, but suddenly your regression coefficients have changed very much, and they're making very different predictions. And this is these high variance coefficients is one reason for rules of thumb, like having at least 10 cases per predictor, 10 to 15 for logistic models, or 10 to 15 samples per predictor for linear regression. Essentially, you need enough data. How do we know we're overfitting? Well, we just check the performance in data we haven't seen. Ideally, we can go out and collect a whole nother data set and see how well that does. If you could do an external validation, you could get another research team on the other side of the world to validate whether your prediction model is working well. But it can be useful to do simpler things first and cheaper things first, and one of which is internal validation or cross-validation. So here we're trying to estimate how well our model is likely to generalize to an independent data set. So in a simple case that we're without any validation, sorry, I'm going to go through a scheme of a few different ways of doing cross-validation here. So in this figure, I'm going to indicate red for data that's used to train the model. Each of these little boxes is an observation, a hypothetical observation. Red ones are used to train the model, blue ones are used to test, and these gradient ones are being used for both. So with no validation, all the data is used to both train and test. But the simplest sort of form of cross-validation is just to take some subset of your sample, randomly select some subjects, don't use them to fit the model, refit the model on this portion, the red data, and see how well they predict the values in the ones they didn't see. In this case, this is a 50% holdout we're illustrating here, because half and half is being used, but you can have other proportions. This is good, perfectly valid, but it is a little inefficient. So it doesn't make the best use of your data, and it can be quite vulnerable to variance. So happening to find a lucky holdout fold that performs better than others or is unrepresentative, that can be a problem. And which comes to the idea of repeating the cross-validation process. So at one extreme, you can have the leave one out cross-validation approach, where essentially you take each subject one at a time, hold them out, fit a new prediction model to the remainder of the data, and see how well it does in your one left out subject. And then you do that. So each subject is left out once, and then you can summarize the performance over the whole sample. That would be your leave one out CV estimate of the generalization error. Yes, sorry, that's illustrated at the bottom there. So it's done for each subject in turn. And there are problems with this as well. I probably won't have time to go fully into it, but the criticism is that it's in the long run, it's a high variance approach. So when you collect a new sample, the leave one out cross-validation error can be variance can be quite different from sample to sample. And this is because the prediction models using the red data are all necessarily very highly correlated. So what's recommended by certain authors is to strike this balance, this k-fold cross-validation. So you split your data into a number of folds. In this case, we're talking about 5 folds, and the process is repeated. The subject in the fold are held out, the model is trained in the other folds and tested in the held out data. So these are all estimates of the cross-validation, the generalization error. As I was hinting on the previous page, but I'm not actually going to go into, but there's advice that you can use a middle k-fold, between 5 and 10 on the k-fold, something in between high k or the leave one out approach and the sort of 50% k in terms of trading off variance and bias. So this is the general idea of how we can diagnose we have overfitting. When the cross-validation shows that the performance is substantially lower than you see in the data used to train, then you probably have some overfitting. We have to think about some practicalities when we do cross-validation, and certainly when I was first exposed to this, these are some things I was initially misconceived about. The performance of the folds have to all be considered together and on average. So don't report the performance in a single best fold. It's a property of all of them. Also, all this work you do, the models you fit in the cross-validation are not used beyond the cross-validation. When you have new data that arrives, the model you use to predict the outcome for that new data, it should be the original model fitted to the full data. Another important thing is the sample size affects the interpretation of K. So bear in mind that if you have a small sample, you may need to choose a different value of K to have enough subjects to train the model or to test the outcome. And I think this is really the key thing. In order for the cross-validation to validly assess the generalization error, you need to have completely independent the holdout fold needs to be completely independent from the training of the model. Otherwise, you get this information leak between the two. So it's probably best to give an example here. So a classic example is pre-screening for significance. Say you have a very large number of predictors and you're not sure which one should go into the prediction model. A common approach is to say, well, if you look at it on its own against the outcome, is it associated or not? And if it's not, then we won't consider it for the prediction model. And this is a fine approach, but if you want to cross-validate that, then you need to do that selection within each loop within each fold of the cross-validation. So each time you run cross-validation, you need to repeat the process of screening the variables. Otherwise, that variability is not captured by the cross-validation process, and you will get an optimistic bias in your cross-validation results. As an example of how this can be a bit more subtle, if you are standardizing predictors, say to put them all on an equal scale, this can also leak information if you do that on the basis of the full sample. What to do if there is overfitting? So we can diagnose if there is overfitting, but what do we do if there is? For example, say we fit a logistic regression to a data set. It happens to be at high risk of overfitting. We've got a small sample, lots of predictors, but we're pretty convinced they're all interesting predictors. Say we observe the accuracy in the training data is 90%, but when we apply the cross-validation, it's not performing anywhere nearly as well. So this 30% drop here from 90 to 60 would suggest, given the circumstances, there's probably some overfitting. I think the common advice, certainly what I've come across and I think this is an excellent advice, is to collect more data to match the complexity of your model. And if you can do this, I think you should, but it's not always possible for practical reasons. Another idea is to simplify the model by removing predictors or terms from those predictors. But care is required here, because we come across the same problem just mentioned, that in order for your cross-validation accuracy to actually reflect the generalization error of the whole process, you need to include the whole process. So this simplification has to be done within the cross-validation. Another issue, even if you do correctly do it within your cross-validation, it's a bit all or nothing. So with this approach, when you drop a variable, it's gone. It's either included or excluded. But the actual best solution to the prediction model might be to include a predictor, but not as much. And this is where regularization comes in, which is a more modern or more sophisticated technique to try and simplify the model. And it's a data-driven way, so it fits nicely within cross-validation, and it's continuous. So you're not either in or out. There can be partly included as well. By regularization, we're talking about making the prediction model more regular, more smooth, with reduced complexity, essentially. It comes up in a lot of different fields and contexts. Sometimes it's called regularization, or it can be penalization, so adding a penalty to a complex solution, or it can be called shrinkage towards the added information. The information we're adding in this case is that the coefficients of the model shouldn't be too large. It also has links in with priors on coefficients in Bayesian methods as well. So the simple idea is, if overfitting has a tendency to make our coefficients high variance, often too large, we can combat this by shrinking them towards 0. This means, though, a regularized model does not make the best predictions for the training data. That's the unregularized solution. That's what it does. It makes usually the best predictions, but the regularized model can generalize better and show better performance in new or unseen data. In the example before, we saw 90% dropping to 60%. Maybe with a regularized solution, you might be able to show 80% down to 75%. So you've got a better performing model when you look outside the training data. An early idea for regularization was heuristic shrinkage, where you just calculate your model and then you say, oh, well, the coefficients are all a bit too large. Let's multiply them by a simple single factor. So they should all be 80% of what they are. And it's not a bad idea, and it did approve, it will improve generalization. But a more sophisticated idea is to say, we will include this regularization budget within the model fitting process. So we now are solving, instead of the prediction modeling, solving what's the best set of coefficients. It's what's the best set of coefficients to predict the outcome within a certain complexity budget. And this figure here shows a regularization path for a particular model. We have different predictors in the model there. At this end, we have the unregularized solution, and at the other end, we have this completely regularized solution. We have no budget for complexity. And you can see that not only do the predictors change in their value, so the coefficients get less as you regularize more, but they can also change their relative position. So their relative strength within the prediction model. And for some, you even get a change in the direction of the effect. What's also here on this line, which I'll talk about in a second, is this red dotted line, which is what we've identified as the best amount of regularization to include. So there's a couple of options for regularization, and they really seem very simple at first. All that changes is how the complexity is defined. Do you define it as the sum of the squared coefficients, or do you define it as the sum of the absolute value coefficients? But this has quite substantial properties on how the regularization path works. So The first option with the sum of squares, the ridge regression, is very helpful with correlated predictors, and when you have a very large number of predictors relative to your sample size, while the lasso has this fantastic property of variable selection. So it has a tendency to, as it regularizes, as it reduces the coefficients values, has a tendency to set them to 0, which a coefficient in a model that's set to 0 has effectively been deselected and is not relevant to the prediction outcome. And this sparsity of the solution is a really important property for the lasso, and really desirable, because you get a really a simple solution as well as a regularized one. So it's not without problems, though, and the elastic net is a compromise between the ridge and the lasso that contains a balance of the two penalties that has the favorable properties of both and none of the strong disadvantages in theory. But it means, as well as deciding how much we need to regularize, this lambda coefficient, deciding where along the lambda path do we use our coefficients to predict, we also need to decide how much of the lasso predictor do we want and how much of the ridge regression do we want. So this is the coefficient alpha. And these are hyperparameters of the problem. So hyper as in above and beyond, and the settings of the hyperparameters determine the model coefficients, really. So we've reached the conclusion that we can combat our overfitting by regularizing. The elastic net has all these favorable properties that will help us decrease our generalization error. But we now have an additional work we need to do, because every time we run a regularization, we need to decide the type of penalty and the amount of penalty we use to make our prediction. And this process of deciding the hyperparameters is often called tuning, and essentially we just explore a range of different values and pick the one that performs the best. Of course, this becomes its own problem, because the best performing hyperparameters shouldn't be judged within their own sample. You need to judge it based on how well they generalize. So you may well tune to the peculiarities of the sample, and we need to use a generalization error to decide the best hyperparameters. So we end up with a second round of cross-validation. So this is the process. We can split the data into folds, determine the combination of hyperparameters that is best for the data, and use that. But we still need to estimate our generalization error, the out of sample prediction performance, and now the selection of alpha and lambda is part of the model fitting process. So this means that we need to run a double cross-validation. We need to make our selection of the hyperparameters independent of our determination of the generalization error. And one approach to this is the nested or double cross-validation. In this, we have two loops. If we start with the outer loop here, this is the blue coded in this diagram. We are interested in calculating the generalization error with the blue data. So we take each fold of in the outer loop, separate off our test data, our held out data, so it is not fed into the hyperparameter tuning. We put the rest in, we run a second cross-validation within that to decide what values of alpha and lambda we use, and then apply this to you generate predictions for the held out data. So in this way, we have we get simultaneously we get generalization error and select regularization appropriately to best give us our cross-validated, our generalization error estimates. So I've established, hopefully, why we're doing this. This will help us produce prediction models that cross-validate. why is there a need for software? And really, it's because we couldn't find what we needed out there without a lot of programming expertise. So the idea of using these regularized solutions has become a lot more attractive since the introduction of the glmnet package, which has a very particularly fast algorithm for this process. And because we need to do double cross-validation, you need a very fast algorithm, and glmnet provides this. It's really excellent, but it's not enough to meet our needs. It doesn't have the double cross-validation. It doesn't allow us to tune. It doesn't allow us to decide between different values of alpha. So you have to decide whether you want ridge or lasso or somewhere in between, and how much you have to make that decision a priori. Whereas we want to probably decide that automatically as part of the tuning process. It also lacks features for exploring the results in a prediction modeling setting. So there are other ways to approach this through more general machine learning sort of toolboxes, but all of them required quite substantial programming skills and background knowledge, and in order to make the sort of appropriate choices to get the valid inference out. So this is what we set to address with dCVnet. We implement double cross-validation. We use the repeated calls of this glmnet package, and we fully tune both alpha and lambda hyperparameters. And we do this in a way that's actually better than most general machine learning toolboxes, because it's set up specifically for these particular hyperparameters. It's not a pure grid search, because you want to test to use different lambda ranges for each value of alpha. Also, we have an outer loop that applies the selected hyperparameters, and it produces detailed prediction performance that other software doesn't always output automatically. We will save a production model, so you can use this for subsequent prediction. And there's a logging feature, so that everything will be written to an Excel file you can use to sort of share the results conveniently. Also, in what I think is an improvement over glmnet, it doesn't just work with a matrix of numbers. You can use the R formula interface to model your variables on the fly. Sorry, to modify your variables on the fly. So if you want to log transform a predictor, you don't have to do that separately and input log transform data. You can do that using the equation. You can also easily include interaction terms this way. So at this point, probably could have a pause and see if there's any questions, but I'll go on to actually how you use the tool if people are interested, or any questions.
Thanks very much, Andre. Yeah, so that's a good thing. It was a great tour on the theory. Any questions about the theoretical basis for this, and what makes it different from just using our tools available?
Well, save that for the discussion then.
Okay, perfect. Yeah. So
yeah. So getting started. I mean, part of the reason I mean, I really like R, but most of the reason we've done this in R is this will work on any platform. So Mac, Windows, Linux, you can install R. It's freely available. You don't have to pay for the licenses. I recommend using RStudio as well, if that's appropriate. But if you're running this on a server, it's no problem to just use R. This shows the commands here. I'm using the caret here to indicate the command line. So download and install R and RStudio. You can install from GitHub, and then run library. Makes it available for the commands available to work from the command line, and this runs a basic example so you can test its working. If you want to see full instructions, that's on the README file, which is the front page of the GitHub. And if you're not familiar with R, I can really recommend software carpentry lessons, which cover using R, Python, GitHub, things like that, particularly for scientists doing research. So This is what I would hope you will see when is that running?
I think not yet.
Oh dear. Oh, this worked earlier. Typical. Let me try again. Well, okay. I will move rapidly on. Sorry, if you run the example, it works. It will start quickly showing output on the console. It comes up immediately with a running loop 1 of 1, and you get a running count of as the software runs. So if you want to run dCVnet on your data, the input is relatively simple. And if you only need to use the default settings, you just want to provide a data frame or matrix of your predictors, and this can be imported really easily from SPSS or Starter, from CSV. You can do everything in another. You can do all your treatment of predictors in another piece of software and import it directly into R. It also needs a separate outcome vector. It would be nice to have kept this within the data frame, but it's difficult to do because we're going to support different families later. So because things like Cox models need a survival object as the outcome, it makes sense to separate the outcome from the predictors. So the key thing is that these line up correctly. So each row in your outcome, in your data frame of predictors, is related to the same appropriate row in your outcome vector. And then you can use the formula interface to specify what you want to be used in the prediction model. This is something that's a really powerful feature of R that if you're not familiar with, you don't have to touch. You can just use tilde-dot, which will use all the predictors in your data.frame or matrix. But if you do get into it, this allows you to do things like specify all second order interactions between variables very flexibly. There are optional.
Sorry, Andrew. I think somebody said the laser, the mouse pointer creates problems for. Yeah, it was something in the chat.
Oh
so
yes.
maybe,
Okay. I'll switch back to cursor. Apologies there. Yes. So there are other options we can set as well. We talked about the cross-validation. You can change options related to the cross-validation. You can change how the hyperparameters are searched. This will vary to a degree from problem to problem, how many lambdas you want to consider, your alpha values. Also, it depends on how much computation time you have. So these are worth tweaking, but the defaults can work quite well in my experience. And then how the best hyperparameters are selected can be done in a number of ways. You can either choose it based on the model deviance, there's the classification error, the area under the curve, and then the key option, I suppose, is this idea of making the model simpler than it would otherwise be. So rather than choosing the absolute best combination of hyperparameters, you pick a combination that's within one standard error of the best, and that might generalize better. But that's I'm not sure of quite what the theoretical background for that is, but that's something that the glmnet authors recommend. So this is an example call, and I would recommend sort of starting from this basis. So we run the model here. The R uses the arrow here as an assignment operator. So the dCVnet function, the results of this function are being assigned to an object, an R object called myModel. And that myModel, the object you assign it to, is all you need to save your results completely and regenerate anything at a later date. So I think what I always do is I save the model to a backup file, and then at any point you can reload that and your computation time isn't lost. Log results to Excel will create the log that I mentioned a minute ago that sort of saves all the relevant data in a sort of an easy to scan multi-page Excel file. But then there's R commands to look at the same aspects, and this is showing how to create a rock plot. So I've mentioned this is very basic. There's no options being set here. If you want to see what the default options are, you can get the help at any time by typing the question mark and then dCVnet, or clicking through the help functions. And by default, we're going to run 2 times repeated tenfold outer cross-validation and 5 times repeated tenfold inner cross-validation. And that may or may not be right for your model. The output you get will then look like this. You get a report saying how long it took to run. This is a particularly trivial example of perfect separation, so the actual numbers are not too important here, but it tells you how many input features there were, how many observations, what the different levels of your outcome variable were, and what you set the hyperparameter tuning to be. You then get information about the cross-validation, the 3 times k-fold and 3 times tenfold in this case, and some options are printed up. You get your final, this is the cross-validated performance. As I say, this is a case of perfect separation, so it does very well. This is just a selection of the actual measures that you get with the full summary and that are written to the log file. We also see some tuning information. So this is showing what tuning parameters were selected, how much regularization was chosen. This is mostly for work if there are any problems. This isn't typically important information. And then the last time you get, in the last section, you get the information from the production model. So this is the final model that you would use. And this kind of tells you, this tells you whether you are, there's a big decrease in performance, and there often is a decrease in performance between the data it's fitted to. It also tells you the hyperparameters that were chosen in the actual production model.
What's CVM? What's CVM? So,
oh, apologies. Yes. So I should say CVM is actually it's the raw format of GLM that we get this from, and it's CVM is the cross-validation measure. So it's whatever metric you chose for the inner loop. In this case, it used, I think, model deviance. Hyperparameter tuning, optimizing deviance.
Yeah.
So if you chose AUC, then I believe the CVM will be the area under the curve.
Yeah, just for the clinicians, I think the area under the curve is what Daniel always told us to use for importing these models, because that generalizes across different sample sizes. So the area under the receiver operator characteristic curve, but you might have some examples later.
Yes, yes, definitely. Okay, so just to go over again some of the output in the Excel log file, you'll have all the information required to work out what you did and why. So it has the call to the function, the options you specified, how long it took to run, and descriptive statistics for the input data, which actually can be very helpful if you get suspicious results. If it looks too good to be true, sometimes the problem is that maybe there was a transformed version of the outcome in your predictor matrix. Something you weren't expecting was inputted as a predictor, and if it looks terrible, then maybe the data wasn't right, but the descriptors can help pick up those sorts of issues. You'll get your classification statistics. This is the average taken over the outer loop. So these are validated, cross-validated, as well as the ones I showed earlier, and as well as the ones here. This is the a standard output from a package called Carrot, which produces a lot of different interesting classification measures: sensitivity, specificity, positive predictive value, negative predictive value, precision recall, all these ones. We also have the AUC, the area under the receiving operating characteristic curve, the Bria score, calibration details, the intercept and slope, all of which can be useful in working out what's going on. I should add that this is all quite extensible as well. For any model, you can extract what's called a performance. The verb we use is performance. So if you run performance my model, you will get a raw data set out that you can take to Excel. You can manipulate further in R. You can do what you like with it and calculate any prediction measures that you would be interested in from the raw data. There's also the classification table. So this is showing on average what proportion of subjects were classified correctly. There's information on the hyperparameters and the variability of the classification performances over the outer loop, which can be useful to tell sometimes if something's not going well. As well as I was saying, this descriptors for this final or production model that you would be using to make new predictions. And there's a variety of plotting options, particularly tuning plots. So this can be helpful if the results are not as expected. If they're particularly good or particularly bad, it's worth having a look to see whether the tuning's going well. It's probably worth having a look to see if the tuning's going very well anyway. But this shows as you move along the amount of regularization within one of the outer loops, how does it pick the best lambda? Is it coming up with the same answer each time? I think there's a zoom in here. So this is using the +1 standard error. So each of these triangles is showing 1 standard error above the actual best value. So the lowest deviance is the best fitting model. We take 1 standard error above, and the different colors are different alpha values here. So this can help get a picture of whether the tuning plot is smooth, whether it's reliably finding a minimum value. And you can also look for individual replications. You can look for individual folds as well. So this is showing in some detail what's occurring. I think in this picture you can see there's one particular repetition that's quite different from the others. Actually, no, sorry, there's one fold that's different from the others in that particular random assignment of the subjects to 2 folds. So there's some other, there's a variety of different ways of exploring the information. Some of this is in the log file. Some of this you have to run in R itself, but you can attempt to explore predictors to see which are particularly relevant. This is showing the absolute value of the standardized beta. So I think this is example data, but it's showing that X4, X10 are particularly important. X25 is very reliably coming up as larger than 0. You can also look at how well your prediction models within the cross-validation are doing at classifying individuals. So this is individuals sorted by their probability. So and it's showing that there's a substantial proportion of the sample we're always classifying correctly, and then these ones they're less certain about. There's a very small number here which are never classified correctly. We can also generate ROC curves, and this is the results from our recent paper, and this shows the average ROC curves over the outer loops of the cross-validation, and in this case we're comparing we're comparing the ROC curves from different sets of predictors, and I will come back to that later, hopefully. But the general recipe for dCVnet is first to prepare the data, particularly to make sure R's interpreting the data right. You need to make sure that it knows what's an unordered factor, what's an ordered factor if you have those, an ordinal factor. Are the continuous variables definitely numeric? Once that's sorted, you're most of the way there. But then the really key thing is deciding which predictors will be included in the model, because as I've sort of said, that if you do your model selection outside of the cross-validation, it can bias your generalization error optimistically. And I think if you see the paper, there is a large section about how we chose each individual variable that went into the model, how it was selected a priori, not on the basis of this data set. So if you use your data to choose your model, you have to do that within the cross-validation, and that's not that's only supported through the lasso approach to variable selection here. So a key thing is to basically decide your predictor variables and how they will be transformed, if there's any nonlinear relationships or interaction effects, and decide that first and make sure it can be justified. Another issue particularly important if you're going to look at classification metrics is to make sure the reference level of the outcome is set correctly. So if R thinks that your levels are controls and are patients and controls, then the sensitivity will actually be the specificity and vice versa. Another issue to think about before you start using dCVnet is missing data, which can't be accommodated by this model. So when you input data, you don't need to remove it, but dCVnet will enforce complete cases on the input. So any missing data will be removed. So any imputation will need to be considered, or whether complete cases is appropriate will need to be considered beforehand. Then really it's as simple as running dCVnet with the default settings, saving the model, inspecting the results, and usually that's enough. The default settings do seem to work in a lot of cases, but if it's always worth checking the results, the tuning plots, check the Excel log to make sure that it was all running as expected, and there are things that can be done if there are obvious problems with the tuning. So particularly this is about changing the range of the hyperparameters, so to consider more lambda values, and doing more repetitions can help if there's variance from run to run of the software. So here's an example changing the cross-validation options. So now we're using much smaller folds and doing many more repetitions. So nrep, outer and inner, set the number of times you're averaging the k-fold estimates. And this can really help if there's a sort of, if it's having difficulty finding reliably a value of the hyperparameters to settle on. This here, setting nrep outer to 250, means that you will be getting should be getting very stable results. So running dCVnet twice will not give different results based on a lucky fold. In fact, what you're doing here is going to be almost building up a distribution of what the results might look like under different initializations of the k-fold. Another possibility is that you have you need different tuning. So in this case, I think this might be suitable if you were interested, if you had many predictors, but you knew that many of them would be not particularly of interest. So choosing a larger value for the number of lambdas increases the resolution that you have to determine the best hyperparameters. And you can set the alpha list to just the lasso if you're reasonably confident that you only want lasso solutions. So the software is pretty well documented. We've got help for everything. There's README files. There are vignettes which show longer examples. And if you do install the package and have a try with it, the vignettes are a good place to start. On the GitHub, if you have any issues, there's a place for that. Please come and post in the issues tab. If you have anything to contribute, you can submit a pull request or send me an email if that's not quite how you work. It's probably worth highlighting performance. So I think I've said that this is fast, but it's fast relative to software that does the same thing. So we run it. It runs very efficiently compared to other software, but it's doing something that is innately very computationally intensive. So the larger your problem size, observations and predictors, the longer it will take to fit. If you need to look at a lot of lambdas, if you want to look at a lot of tuning values for alpha, it takes a long time. And then you have to multiply that by the K, the cross-validation factors, the number of folds you're looking at and the number of times you're repeating it. So it scales a little poorly. And it can be a bit confusing to set how many repetitions you need. In general, more is better, but I find it's very easy to come up against computation time problems or where it feels impractical. But if you do want to build up a distribution and do this many times, thousands of times potentially, the outer loop is fully parallelized on Linux, and I'm working on an easy way to get that going on Windows, but I find most people don't want to have it running on their Windows computer for a long time. So I think most people who would run this for a few days would do it on a Linux box. But as I say, this is faster, hopefully, certainly in the test that we've done. When we implement the same thing in a general machine learning toolkit, we're a little bit faster because we're tuned specifically to this problem, and the glmnet package is particularly fast. So wrapping up, I think this is really useful if your goal is prediction and you still want a model that's a bit explainable. You're not going into a full glass box, a non-glass box model. Black box, that should be. So you still have explainable coefficients. You can work out exactly why you're making the predictions you are. If you think that an unregularized model is maybe overfitting in your sample, this can really help. It works perfectly with multicollinearity and correlated predictors. So in a traditional logistic regression, you wouldn't put in two highly correlated predictors. There's no problem doing that with this approach. It works if some variables may be completely unrelated to the outcome or maybe better explained by other variables in the same set. And you can have any mixture of continuous and categorical predictors. That said, it's not particularly useful if you mainly want to know about the model parameters. If you want to say this particular predictor is associated with the outcome, it's less useful than potentially doing as a more standard inferential analysis. If you have big data, this can be too computationally expensive. And if it's very likely that your predictors are very substantially non-linearly related to your outcomes, if you don't know the approximate form of the relationship, then that could be a suggestion that you want something different than dCVnet. Also, it very much doesn't cope with hierarchical models or time series. So if you have dependencies between your observations, correlations, that can be a problem. Missing data is somewhat of an outstanding question, and maybe we can talk about that a bit more in the discussion panel. But thank you all very much for listening. I hope that was interesting. I want to finish by acknowledging the fantastic help of Daniel, of Roland, of Paola, who are all going to be on the discussion panel, but also the very helpful conversations I had with Deborah. And yes, the R language and glmnet package authors, without whom none of this would be possible.
Thank you so much, Andrew. I just realized that I think we haven't introduced Deborah yet. So Deborah, would you like to introduce yourself? That would be great.
Oh,
is
Daniel,
Deborah?
I think you're muted. I'm not sure if she's here today.
No, unfortunately, Deborah left our department. She's became a school teacher for maths. So
oh wow!
Decided to quit academia, and we only collaborate now with perhaps teaching.
So that's a very worthy question. So sorry, I suddenly thought, have I forgotten something?
Oh, so yeah, sorry, Roland. I had very valuable conversations, and I hope that wasn't what put her off an academic career.
No, dCVnet.
We tried our best to keep her, but decided to become a school teacher. So.
Yeah. So I certainly would have needed better school teaching for maths.
Yes, I think very good.
So thank you so much, Andrew. I think it's been fantastic to get that overview, and now it's really an open discussion on any aspect of. So it could be practical questions you might have, or theoretical questions. What's the difference between machine learning and this approach, or is it a type of machine learning? For example, you could ask about clinical applications, and anything you like. You can either put your question into the chat, or you could just open your mic and listen.
Hello, hi, can you hear me?
Yes, hi.
Hi, yeah, sorry. Sorry, my name's Laith. I'm just one of the junior doctors who just started here, so my statistical knowledge is quite rudimentary, but if there are lots of categorical continuous variables, would you ever sort of recommend doing some form of like dimension reduction prior to putting your data into this dCV package?
I think that's a really good question. So in some ways there are links between regularization and sort of PCA style dimension reduction. So I believe that there's a link between particularly the ridge solution and PCA regression. That's where you take your data, you run principal components, and then you include the principal components in your model instead of the original predictors. So my understanding is there's some links there. In theory, the variable selection should be enough, or the dealing with correlated predictors and the induction of sparsity, if you include some lasso in the elastic net, it could it could manage, but that's in these things I would guess that if you give it a helping hand, if you know that your data is better described by a factor solution, then giving it that factor solution would be a faster way or more efficient way of getting a good prediction model. But so I would say it depends on your domain knowledge, but I'd be really interested to see if Daniel agrees with me in any way on this.
Yeah, I think I would agree. I think it depends on the question and also on the number of variables you have. So one thing is you should not do any pre-selection based on univariate regressions or correlations. That would be cheating. You would overfit your model. PCA might be useful or factor analysis if you know that you've got a set of variables which are all measuring a similar concept, and you want this concept in your model. But you also have to think about what you want to do with your model, because if you want to have a small set of predictors, then you might want to include all the variables, because otherwise you need to do always a PCA or the factor analysis before if you want to predict new cases, or you need to collect all the data for these people. So if you've got 10 variables and you can basically one would be enough, then for a prediction model you might use elastic net or lasso to identify this most important variable. If you're more interested in looking if a factor is important or a latent variable, then you would include a latent variable, but it would become later more difficult to apply this model in a clinical setting. So it always depends a bit on your research question.
Yeah, that makes sense. Thank you.
Yeah, great question. Thanks. Any other questions about what Andrew said? I think for those of us, including me, who don't have a statistical background, it's quite a lot to take in. You know, after hearing Andrew and Daniel discuss this for years now, I've started to understand what lasso is, but I will forget every time again. But I think one thing, just from my own experience, just using the tool, is that you still need to be careful not to overload it with predictors. So although in theory it should be able to deal with it, but my experience is that I think it does, and we had this discussion, Daniel, didn't we? That there's always a balance to everything, you know, and we're dealing. Of course, we had the sample of 52 people, which is really not very large for this stuff, but it worked. I guess, Daniel, if you've got a larger sample, is that less critical then? Is there a dependency between, still a dependency between how many, what your sample size is and how many predictors you can afford to have, like in regular statistics, as Andrew mentioned, where we shouldn't have more than one predictor for 10 subjects. But is there something here as well?
Yes, I think that's a good question. I think your model depends on the number of predictors or the number of parameters you want to estimate relative to sample size. So if you've got a large sample size, you can include more variables. So the model is not perfect, not a substitute for, well, it's always better to have theory-driven variables in your model, not everything what's available, because the more noise variables include, the worse will be your model, and that this trade-off depends on your sample size. So okay, there's no real guidelines what sample size you need for how many variables. It always depends on how strong your predictors are. There is a new package which calculates the sample size to prevent overfitting by Richard Riley.
All right.
Yeah.
Put that in the chat. Or?
Yeah, I can put in the chat, PMSAM, but it's not developed for regularized regression. It's developed for normal regression, but he suggested also to use it as a guideline for regularized regressions, for lasso or elastic net regressions.
Okay, great.
And it's so the smaller the sample size relative to your variables, the more likely is that you will get false positive results, so false positive variables, so that what Deborah could show, and the less stable is your model. Okay. And a bit of the instability can be seen by Andrew's, if Andrew, in the area on the curve, how it differs between each of the outer loops. So if the outer loops, the area in the curves very, very little, then you have got a more stable model than if it range from 0.5 to 1. So that's why Andrew's model is very useful, because most other programs don't really show this. You have to compute it by yourself, and that's rather difficult.
Thanks very much, Daniel. I just see Sandrine has her hand up. Sandrine, do you want to ask your question?
Thank you. That was really useful, really clear talk, especially for people who are not specialists, but are using similar tools or have this type of questions. So I always have in my lab, we always had collaborated with biostatistician to do this type of analysis for us, and as of course we understand more and more better from them, this is nice then to see this tool that we might even be able to run ourselves even before to discuss with them further to see is this appropriate, or to have an idea. But maybe one first simple question for me was, so is this tool, could you see using this tool for in a validation cohort? So let's say you have already a model would you think that this is acceptable to use this tool in a validation cohort and run your cross-validation in this validation cohort?
That's a
great question, Cedric. So, Andrew, do you want to answer that, or Daniel?
I think the real strength in the applying the regularization is that it should make your model work better in the validation cohort. So I would think it would be most useful applied before. Yeah. So in order to choose slightly more modest coefficients or less extreme coefficients that would then be more likely to get you a better result in a new cohort. But one of the things I didn't really touch on was that external validation is the gold standard, and you can get sort of things like I've heard it described as covariate shift, but essentially it can be a moving target, and it's in particularly in, well, where I work in MRI, you move to a new cohort, you get a different scanner. Sometimes the measures are not as reliable, or there are these can be unusual biases. It's very difficult to do multi-site scanning, and the regularization may not be helping with the reliable features from one site to another. So in external validation, you can get extra sources of problems with the prediction model. So yes, this will definitely help with overfitting and with these having too extreme coefficients, but and I would hope that would help with external validation, but not necessarily.
Great, we will try. We'll see what we get, because we have indeed a study where we did similar approach with some cross-validation within the same cohort, and now have another cohort where we are going to test our model, and it would be interesting to run this there.
Yeah.
Can I ask another question?
You could do a parallel evaluation, so you could refit your model with dCVnet and see if that helps. I think this is
what we should do. Listening to you, I think we should revisit our data and use our model and see what we get as well. Can I ask another question regarding to Daniel's comment? Andrew, you mentioned that we should decide on, let's say we have a new cohort. I'm not talking about validation. We have a new cohort, and then we need to decide on predictor variables. But then Daniel told us that, well, you can't really look at regression or other data to decide on these potential predictor variables. So how would you choose, if you have to limit the number, how would you choose the number of predictor variables to not cheat, to quote Daniel?
Well, what the best is to look in meta-analysis about known predictors or on the literature. So everything
so like an educated, I mean, for us, I'm a biologist, neuroscientist. So we chose our predictor on the biological relevance. So that's fine.
Yes, you can also use clinical expertise. In if there's a variable that people assume that it's important, then of course you could include it.
No, absolutely. Yeah.
But I mean, if you use clinical databases, you might get hundreds of variables, like blood variables.
Yeah.
If you assume that none of them is really important, and then it's better not to include them.
Absolutely. Yeah.
Especially if the sample size is small.
Okay, great.
But if then assume that one hormone might be important, then of course I would include it.
We can include it, on the biological reasoning that it makes sense. Yeah. Okay, great. Thank you very much, everyone.
Thank you, Sandrine. I think this is what I like about this approach. It's still, your natural intelligence is still relevant, and your hypotheses and your conceptualization of your scientific problems. So it's not this black box type of machine learning. There's another question by Jonah.
Hi, how's it going?
Hi.
Hi, Andrew. It was a brilliant talk. Great. I hope to use the model sometime. It seems really great. I just had a question. You mentioned pipelines throughout your talk, and at the end there you mentioned problems with imputing missing data as well. I was wondering if you could comment on that. I'm presuming pipelines would work as they would for glmnet, and if you could just elaborate on your thoughts on dealing with missing data.
Yes. So this is something we've come up with. We've come against. So we have worked with missing data for this. The difficulty is, and what I had some discussions with Deborah, which were very helpful, is the right way to do it is computationally very difficult, or I say the right way to do it. What I came to was that multiple imputation would be very nice to have. So I don't know if you're aware of the mice package, where you do these sort of recursive generation of the related variables in the model to produce multiple imputed data sets, and then you pool results over several different versions of the imputed data sets. But if you need to do that within each cross-validation loop, and you're it's impossible. So I find even for quite small data sets, it can take sort of 15-20 minutes to produce the multiple imputations, and for another option is Miss Forest, which only generates one data set, but it still takes a long time to fit. And so if you need to do this within each cross-validation, so each fold, each repetition, you would be there forever, even for a very simple model. So I think it has to be done outside of the cross-validation loop, and that means that it then can't be included it can't be considered in the generalization error in a way. But we did manage to do it outside. Essentially, you run dCVnet on your however many imputed data sets you get. We didn't have a lot of time to validate it, but it's possible to work with multiple imputation. And if you use Miss Forest or something that's a single imputation, it's very much possible to work with that. But what you can't do is practically account for the variability in that within the cross-validation loop, if that makes sense. So there's the initial question of, is your data suitable for multiple imputation anyway? Is the missingness pattern correct or appropriate for MCAR? But that's a sort of a separate issue. And yeah.
Okay, great. Yeah, no, I hadn't expected. Yeah, the mice obviously would be extremely difficult to run together with that. But I'm not as familiar with Miss Forest. But would you know if something like KNN imputation would work within the cross-validation folds, or?
Daniel, do you want to comment? So Deborah was a big fan of Miss Forest, and we've used that in the department, but not particularly me. So if I can pass that to Daniel.
Sure, thanks.
So we use both KNN, so K nearest neighbor, and Miss Forest. At the end we preferred K nearest neighbor because what the idea is, you have got your training data and you fit a K nearest neighbor model which imputes the data, and then you use this imputation model to impute the data in your holdout data set. So there's no leakage of information, and that worked pretty well if you don't have too many missing data, because K nearest neighbor needs, I think, 60% complete cases. Miss Forest does not, you don't get an imputation model which you then can predict in your holdout data set. That's a disadvantage. You can predict, make prediction within the training data set and in the test data set separately in Miss Forest, but then you need a large data set in your holdout data, in your test data set where you impute with Miss Forest. So there were some studies which suggest that this is an acceptable method. But the best is if you develop a model within your training data and then you fit it in your holdout data set. And that is in Carré, you can tick the box in Carré, which is another wrapper, which I don't know if if you use it, Andrew, which does it automatically, but only for continuous data. And we used it for a mix of data, but we had to program it by ourselves, or Deborah did it. And yeah, it works well if you don't have too many missing data. But it's a general problem, and it will be a topic in the next BRC theme in our.
Okay, great. Thanks very much. That clears things up. Great work. Thanks, guys.
Thank you.
So I think we've got only 5 minutes left, but it's been fantastic to see so many of you actively engaging with this really difficult topic. And thank you so much, Andrew, for this fantastic presentation. I was just wondering, Paola, do you have any final thoughts on, the clinical perspective or where you think this prediction modeling is going, how it's going to shape our world as psychiatrists? But do you think it's going to change the way we look at risk prediction and how we also communicate risk to our patients?
Thank you, Roland, and thank you, Andrew and Daniel, for a wonderful presentation and discussion. I think as a clinician, I'm certainly one of those that has really wish we had more of reliable instruments that would allow us to make such good predictions that we could use them when we are sitting there with the patient in front of us, and we haven't achieved that yet. But I'm confident that if we improve the way in which we use prediction, hopefully we will be able to make predictions that are above the ones that we can already do based on our usual list of risk factors that we use for prognosis. And I think one of the things I've really liked about this work is that it has really addressed a lot of the challenges and issues that we have had with previous approaches that we've used for, statistical approaches that we have used for the application to clinical predictions. So I'm very hopeful. I really like this tool. Like you have had extensive discussions with Andrew about the applicability of this method, the limitations, and the interpretability, because I think one of the problems that especially the people who are not statisticians like myself have is with getting the numbers at the end of the run and really thinking what do they really mean and how we can use them in real life. So I think it's been a fantastic trip to get here, and I think it just shows what amazing work can come from an infrastructure support-led one offered by our BRC. I think this is a clear example of how different groups can work together in generating an instrument that is there to stay, that it just hasn't served the purpose of a single analysis or a single project, but has created real infrastructure for something that is truly translationable, like this tool. So thank you so much, Andrew, Daniel, and Roland, and the multiple conversations we have all had along the years that have brought us here. And thank you to our fantastic BRC for this. And thank you all for attending today and the stimulating discussion.
Thanks very much. Yeah, and again, we will put the recording on the event page, and you've got all the resources. And just also a final remark from my perspective, I think my take-home message from working with Daniel and Andrew on this is that as clinicians, we give inaccurate and misleading information to our patients by saying, for example, oh, there is a risk, this is a known risk factor for this. For example, recurrence prediction in depression, very important decision. Should you stop your medication after recovering, yes or no? Basically, we say to people, according to the NICE guideline, but based on how many episodes you've had in your past, you should continue for half a year or 2 years. And actually, if you plug in the number of episodes you've had in your previous history into the model, it's basically like flipping a coin. Although it's highly significant in a general statistics sense, it's worthless as a predictor at the individual level. And I think this type of thinking we really need to hammer into clinicians, because frankly, I think these significant risk factors can also, if we are enslaved by those risk factors in our decisions, which are still just random at the individual level, it makes our life more miserable. And I'm just thinking all the things that we're not allowed to eat because there's a risk of disease attached to them. So, but that's just my closing remark. I don't want to babble on. Andrew is typing. Thank you so much to everyone. We were very happy to have this lively discussion. And yeah, thanks, Andrew. I think you've done a fantastic job with this, presenting this very difficult thing in such a compressed session. So thanks to everyone. And I think Andrew's going to stop the recording very soon. And